Hello everybody, today's video is a continuation for chapter 7 on coordinate geometry. We will be taking a look at chapter 7.3 midpoint of a line segment. This is a part 2 video. Okay, so the objective of today's lesson is the use of the midpoint of a line segment to find the equation of the perpendicular bisector of the line segment, and also to solve problems involving the midpoint of a line segment. Let us first recall the main concept covered in the previous part of this chapter 7.3, which is the midpoint formula that we have learned. So when we are given 2 points, okay, and we want to find out the coordinates of the midpoint of AB, that will actually abide by this particular formula here. So let us first take a look at our first application. Our first application for the midpoint formula is to find the fourth vertex of parallelograms. If ABCD is given to be a parallelogram, then the midpoint of the diagonal AC is the midpoint of the diagonal BD. Okay, so what are diagonals? Diagonals are lines that go through, okay, cut across diagonally, all right, from vertex to vertex. Okay, by the way, vertex is actually the coordinates over here. Right, this is what we mean by vertex. Okay, so anyway, going back to this about the diagonals, right? So when the diagonals actually intersect like this, okay, it is trying to say that they are going to be equal. Okay, so this is going to be the midpoint of the diagonal BD. It is also the same midpoint for the diagonal AC. Okay, and why this can happen is actually because based on the property of parallelograms, diagonals actually bisect each other. That means that the diagonal AC cuts BD into equal lengths, and then after that BD actually cuts AC into equal length in this manner. Okay, so one important thing is what quadrilaterals are actually considered parallelograms. Okay, parallelograms are not restricted to this manner, right? There are many things that are actually considered parallelograms, right? And that would include things like rhombus, okay, squares, as well as rectangles. Okay, in case you do not remember what are quadrilaterals, quadrilaterals are actually any four-sided figure. So examples of four-sided figures would be things like maybe kite, okay, as well as trapezium. Alright, so kite and trapezium, they do not fall under the category of parallelograms, okay, because they do not have two pairs of parallel lines. Alright, so let's practice with try 10 found from a textbook page 174. It shows a diagram PQRS, which is a parallelogram, in which P has the coordinates, or rather PQRS has all the coordinates as shown in the diagram. So in part I, given that the point M is the midpoint of PR, okay, so PR is this diagonal, and the point M would be here. Okay, we want to find the coordinates of M. So we will use our formula that we have previously learned in finding midpoint, and we get that the coordinates of M will be 3.5, 4.5. Moving on to part 2, we want to hence find the coordinates of S. Okay, so S is actually the fourth vertex of a parallelogram. Okay, so in this application, okay, of using the midpoint formula, what we're trying to do is that we are always going to be given the coordinates of 3 vertices, okay, and we want to find the coordinates of the fourth vertex. So how we go about doing that is to make use of the fact that the diagonals will always bisect in a parallelogram. So even if in a square, that will also happen because a square is a parallelogram. Okay, so because the midpoint is going to be equal, that means that the midpoint of PR, which is what we have found in part I, okay, so this is the midpoint M, the coordinates of midpoint M, right? And then after that, the coordinates of the midpoint for QS would actually be this set of coordinates here. So that means that the X coordinate have to be equal and the Y coordinates have to be equal. And that will actually give us A to be equals to 5 and B is equals to 8. Therefore, we have the set of coordinates 5, 8 for S. Okay, Why is it that we want to go through this kind of method of making use of the midpoint formula? The reason is because if I want to choose other methods such as equating the length of a parallelogram, or to actually find the gradient of the parallelogram, if you were to go through that process, it will definitely be very, very lengthy. Okay, so actually using the midpoint formula and create an equation out of it, it really simplifies the process for all of us. Now in part 3, we want to show that PQRS is a square. Before we talk about this question in terms of how to answer it, we need to think about what actually makes something a square. Okay, so what are the different kind of properties that must happen in order to say that, oh yes, that four-sided figure is going to be a square? So it needs to be a parallelogram. Okay, why do I say that? It is because, oh dear, it is not responding. Okay, it's back. Okay, so it is going to be a parallelogram because when it comes to a square, which I have shown on the right side over here, we know that surely the opposite sides will be parallel to each other. Okay, so therefore we have two pairs of parallel lines, therefore it will become a parallelogram. Okay, or rather it will be considered as a parallelogram. And then another property that we will see that is unique to a square is that all sides actually have the same length. Something else that is unique to a square is that the interior angles are going to be 90 degrees each. Okay, by interior angles, I actually refer to these angles here. Okay, so they have the same length, everything same length. Okay, so can we miss out on any one of these three properties over here and yet still conclude it to be a square? The answer is no, because if I were to just choose, okay, 1 and 2, okay, it is only sufficient to say that it is a rhombus. So it is only at least to be a rhombus, because a parallelogram that has the sides to be of the same length, okay, a rhombus definitely satisfies that. Okay, we do have a parallelogram and all sides are the same. So I can only say that it is either a rhombus or else a square. And then if I were to choose just option 1 and option 3, okay, I will be able to only see that it is going to be at least a rectangle, because having it to be a parallelogram and all interior angles are 90 degrees, a rectangle satisfies that criteria. Okay, so that means it is either going to be a rectangle or else a square if I only go through 1 and 3. Okay, however, if I go through every single option 1, 2 and 3, okay, I will be able to safely say that yes, it must be a square. Okay, so therefore this is the process, or rather these are the qualities that we must check through in order to verify that PQRS is going to be a square. Okay, so this will guide us in our answer. Let us now move on to our answer. Okay, so and back to this question whereby we are given this diagram, okay, and we already found out what is the coordinate for S. So we will first find out what is PQ, okay, the length of PQ, as well as the length of QR. Okay, and we find that PQ is going to be square root 29 and QR is square root 29. I kept them to exact values so that it is easier for me to be able to deduce that they are definitely equal in value, rather than relying on a truncated figure, which may just actually be equal by chance. So you don't want that to happen. Okay, so because PQRS is a parallelogram, okay, finding out what is PQ is equivalent to finding out what is SR. And then finding out what is QR is equivalent to finding out what is PS. Okay, so now because PQ and QR actually equal in length, okay, it will mean that every single side of this figure here are going to be equal in length. So we can say that PQRS is actually a rhombus, otherwise a square. So these are the two options. So we need to narrow it down further. Okay, and to narrow it down further, we are only short of addressing the part on interior angles being 90 degrees each. So how am I going to introduce 90 degrees into this diagram that doesn't give information about the angles? So we will do that by finding the gradient of PQ as well as the gradient of QR. And then by looking at the product of these two gradients, we see that it is -1. Okay, so because the product is -1, that means PQ and QR are perpendicular to each other, or in other words, it means that angle PQR is equal to 90 degrees. So in the rhombus itself, okay, the interior angles are actually not all going to be 90 degrees. So having this interior angle to be 90 degrees, it confirms to us that this figure must definitely be a square. In case you're wondering, okay, saying that PQR is equals to 90, how is it sufficient to say that all the interior angles, every single corner, is going to be 90 degrees? Okay, so what gives me that assurance is actually because of the fact that the question says PQRS is a parallelogram. So if I know that this is 90 degrees already, okay, and because it is a parallelogram, that means PQ is parallel to SR. So I will be able to know that this is 90 degrees due to interior angles of interior angles parallel lines, okay, because 180 minus away 90, I will surely get this to be 90. So by the same concept, okay, because I know that it is a parallelogram, now I will consider these two lines that are parallel to each other. If now I'm sure that angle Q and angle R are going to be 90 degrees, by the same property, interior angles, parallel lines, I will be able to deduce that this is 90 degrees. So I actually need not go about verifying every single angle, okay, because the question has already told us that it is a parallelogram. So we only need to determine, okay, whether are the lengths actually equal, and also are the interior angles going to be equal to 90 degrees. So with that, okay, we conclude that PQRS is a square. We now take a look at exercise 7.3 question 9, where we are given the coordinates of 3 vertices of a parallelogram. So we got these three pairs over here. Okay, then we want to find the coordinates of the 4th vertex. So I drew out a sketch on the right here, okay, with the given information about the different points. Okay, so let us, for convenience, oops, I'm sorry that my computer is hanging again. Okay, so we're back. So for convenience, okay, we let A to be -1, 6, B to be 0, 0, C to be 3, 1, and the 4th vertex we let it to be x, y. Okay, so the 4th vertex, the parallelogram, would probably look something like that. Okay, I guess the computer is getting tired. Okay, so the parallelogram would probably look something like that, where D is somewhere over here. Okay, I'm not too sure. Alright, so let's continue with our working. So because we are finding the 4th vertex and this is part of a parallelogram, okay, that will mean that the midpoints of the diagonals will actually be equal to each other. So what I have here is the calculation for midpoint of AC, and I equate it to the midpoint of BD, okay, where I have x and y being introduced. So the x coordinates will have to be equal and the y coordinates of the midpoint have to be equal. Therefore, I will separate that out, okay, and I see that I will get x equals to 2 and y equals to 7. Answering the question, we want a pair of coordinates, so the coordinates for the 4th vertex will be 2, 7. So previously in the lesson, we have already taken a look at one of the applications, which is to find out what is the coordinates of the 4th vertex of a parallelogram only. So another application of using the midpoint formula is to find out the equation of a perpendicular bisector. So what is a perpendicular bisector? A perpendicular bisector is actually a line, okay, that bisects AB and is perpendicular to AB. So bisect means that it is cutting something into 2 equal parts. Okay, bi means 2. Okay, sect means to intersect. Alright, so that's why we have AM and MB to be of equal length. Okay, and then very importantly, it is called perpendicular bisector. So it got to be perpendicular somewhere. So the line, okay, the perpendicular bisector is 90 degrees to the line AB. Okay. One important property about perpendicular bisectors, okay, that we learned in Sec 1, where we know how to do geometrical construction, is that any point that is found on the perpendicular bisector would be equidistant to AB. Okay, so what this means is that, as a refresher to what you have done in Sec 1, okay, is that if I choose one point over here on the perpendicular bisector and I measure the distance from A to that point and the distance from B to that point, I will realize that both distances are actually equal. Okay, and if I were to select another point, maybe here, okay, and I measure the distance from that point to B and measure that distance from that point to A, okay, these two distances will actually be equal. However, I want to point out to you that the ones that are in red, okay, the lengths that are in red and the lengths that are in green, they are actually not equal in length. Alright, it is only to each other, the one in greens and also the ones in green to each other, right, within itself, okay, that they are actually equal in length. Okay, and that is addressing the idea of being equidistant. Okay, I'm sorry, that is hanging again. Okay, back to this. Alright, and that is what it means by equidistant to A and B. Okay, let us now take a look at some practice examples to work on those concepts. So taking a look at question try 11, okay, we are given that the line 5x plus 4y equals to 20 intersects the x-axis at the point P and the y-axis at the point Q. Okay, so I drew a draft diagram on the right to aid me in visualizing the question. Okay, but since we're trying to find x-axis at point, or rather the point P, okay, which intersects the x-axis, and the point Q, which intersects the y-axis, we will just do our straightforward substitution respectively, and we will get the coordinates of P and Q, okay, to be for Q 0, 5 and for P 4, 0. So moving on to part 2, we are given that the perpendicular bisector of PQ intersects the line y equals to x at the point R. So let us put in some information to our diagram. Okay, so we have a perpendicular bisector, probably something that looks like this, okay, of PQ, right? Then after that, the midpoint between PQ is actually going, or rather the perpendicular bisector is going to bisect the line PQ. Okay, then after that it will intersect the line y equals to x. So maybe the line y equals to x will look something like this, perhaps. Okay, so this is y equals to x, and the red one is the perpendicular bisector. Alright, and then it says that they intersect at a point R. Okay, so this is just a rough guide, right, to guide ourselves. So in order to find the intersection point, we definitely need to know what is the equation of the perpendicular bisector. Then we can do our simultaneous equation solving. I'm sorry for the hanging again. Okay, so then we can do simultaneous equation solving, right, in order to find out the coordinates of R. So let's start with the answer. Okay, we want to let the midpoint of PQ be M, XY. Okay, so this will help us in terms of our presentation. Okay, so XY will be equals to 4 plus 0 over 2 and 0 plus 5 over 2, and we get 2 and 2.5. Okay, then after that, we will find out what is the gradient of PQ, because only when we find the gradient of PQ, then we can find the gradient of the perpendicular bisector, okay, which is the negative reciprocal. So that's why we will get 4 over 5 for the gradient of the perpendicular bisector. So now that I have the gradient, and I also have one coordinate point on the perpendicular bisector itself, I can make use of the equation. Okay, so in case you have forgotten, this is the equation formula, right? So we put in the coordinate points, and then we also put in the gradient, and then it will simplify to be y equals to 4 over 5x plus 9 over 10. Okay, don't forget that this question is asking for the intersection point R. So we will need to do simultaneous equation solving as mentioned earlier. And by doing some substitution method, we will be able to eventually get the coordinates for R, which is 4.5, 4.5. We will be giving part 3 a skip, okay, because there is a slightly more efficient method that we will be learning in chapter 7.4. So I will not be going through part 3. Moving on to exercise 7.3, question 13, we are given that the coordinates of two diagonally opposite vertices of a square are 6, 4 and 0, 8. So I drew a diagram, okay, I sketched out a diagram over here to help me to visualize the question, right? Then after that, in part I, we want to show that 1, 3 is also a vertex of the square. So I place all the 3 points that I'm given into this diagram here. Okay, do take note that when showing whether is it a vertex of a square, I definitely cannot draw a scaled diagram to actually prove it during the exam. Okay, I need to do it in a slightly more rigorous manner. So to aid myself in the presentation, I have decided to name the points A, B and C. Okay, so in order to verify that it is going to be a square, as mentioned earlier, okay, in the earlier parts of this lesson, we have agreed that it needs to be a parallelogram and it needs to have interior angles to be 90 degrees, and also the lengths of the sides needs to be equal as well. So let's just head for the lengths of the sides first. So I will find out what is the length of AC and the length of BC. Okay, why should I not be looking for the length of AB and compare it to BC instead? Okay, because the question has mentioned that the coordinates of A and B are diagonally opposite vertices, so they are opposite one another. Okay, I'm sorry about the lag again. Alright, so that's why, okay, I have to choose AC and BC. So using the length formula, okay, I will be able to arrive at AC being equals to square root 26 and BC is also the same value. Okay, so I can conclude that there are two sides that are actually equal to each other. Okay, then after that, okay, I will look at the gradient. Okay, I will look at the gradient of AC and I find that the value is -5, and the gradient of BC, which is 1/5. And we see that they are actually negative reciprocals of each other. Okay, therefore AC and BC are going to be perpendicular to each other. Now I just want to set you thinking, is there another way to show that AC and BC are perpendicular to each other without actually using gradient? Okay, do think about that. Okay, is there another way to this? Right, I hope that you gave it a thought. Okay, there is actually another way, alright, which is to actually apply Pythagoras theorem. Okay, so answer is yes, apply Pythagoras theorem. Okay, so how do we go about doing that? It is just like in your E-maths, when I want to verify that a triangle is a right angle triangle, I have already found out the length of AC and BC. What I can do is to find the diagonal, or in fact it is the hypotenuse, okay, of a possible right angle triangle, AB. Okay, so I find out what is the length of AB, then I will eventually definitely be able to see that AB square, okay, I will do my working and then I will see that AB square is equals to AC square plus BC square. Okay, and then I can conclude that angle ABC, sorry, not ABC, but angle ACB, right? Let me do a check. Yeah, angle ACB will have to be 90 degrees. Okay, let me correct this. Right, I hope that maybe one of you is able to realize that. Sorry, give me a minute to get my eraser going, and it's now hanging again. Okay, so oops, a doodle happened. Okay, so angle ACB is equals to 90 degrees. So anyway, going back to the main point here, okay, we have already proven that AC is equals to BC, and also AC is perpendicular to each other. So since these qualities seem to happen, surely, okay, we will be able to form a square, okay, out of these 3 points. Alright, so 1, 3 is definitely a vertex of a possible square. Okay, so that is how we actually show and answer this question. Next, moving on to part 2, we want to find the coordinates of the 4th vertex. So since we already have the 3 points going on, we will use what we have learned earlier in this lesson, okay, which is to equate the midpoints of the diagonals, Okay, so I equate them together and I will be able to equate the x coordinate and the y coordinate. Then I will find that x is equals to 5 and y is equals to 9, which are the coordinates of the fourth vertex. And in part 3, we want to find the area of the square. Since we have already earlier found out the length of AC and BC, and it is verified to be a square already, we will just multiply the lengths that we have gotten and we will see that the area will be 26 units square. We have finally come to the end of the last question. Okay, not the end yet, I'm sorry. Alright, the last question of this lesson, which is question 15. Okay, and we want to find out the equation of the perpendicular bisector of PQ when we are given the coordinates of PQ. So to imagine this, okay, so the point P would probably be around here in the set of axes. Alright, and then after that we have maybe Q to be around here. Okay, and we have this line. Right, so we want to find the equation of the perpendicular bisector. Okay, so we need to know what is the midpoint. Right, sorry, let me get the colors right first. No, the color is not coming out. Okay, but anyway, to find out the perpendicular bisector of PQ, we need to know what is the midpoint as well as the gradient, okay, of the perpendicular bisector. Alright, so let us first find out the midpoint, the coordinates of the midpoint. So using the coordinates of P and Q and using the formula, we will get that the midpoint PQ will be 4, 7. Then following from there, we find out what is the gradient of PQ, and that will help us to find the gradient of the perpendicular bisector, which is -1/2. So then we will use our equation of a straight line formula, y minus y1 equals to m times x minus x1, and I will be able to simplify that and I get y equals to -1/2 x plus 9. If you are ever required to write in integer coefficients, okay, then the answer is to multiply by 2, okay, which is the denominator of the equation throughout, okay, the entire thing, and I will get 2y equals to -x plus 18. So either one will actually be acceptable. Okay. And now we are at the very last part where we want to find the coordinates of the point that lies on the line y equals to 6 and is equidistant from P and Q. So if you recall right at the beginning when we talked about this discussion, this application of perpendicular bisectors, okay, is that if I have a perpendicular bisector going through the line PQ, okay, any point, alright, that is found on the perpendicular bisector will actually be equidistant to P and Q itself. Alright, so any point, alright, really any point that is found on the perpendicular bisector will be equidistant from P and Q. Okay, then in this question, we are trying to actually find the coordinates of the point that lies on the line y equals to 6x. So there is another criteria that it must be on y equals to 6x and not just equidistance from P and Q. Okay, so if I were to draw in a line y equals to 6x, maybe it will look something like this, perhaps. Okay, so with this line, okay, to satisfy both y equals to 6x and the fact that it must be equidistant, that would actually mean that we are going to be looking at the intersection point. Okay, and to arrive at this intersection point, I definitely need to know what is the equation of the perpendicular bisector, because after all, I already know what is this green colored lines equation. Alright, so the equation of the perpendicular bisector, fortunately, we have already found it in part 2. Okay, so all we have to, part 1, not part 2. Okay, so what we have to do in part 2 is to just solve things simultaneously. Okay, so the big challenge in this question is to realize, alright, what does it mean when a point is actually equidistant from P and Q? So where do we find this point? And the answer is to, okay, my pen battery is low, right? The answer is to actually look for the point on the perpendicular bisector. So going back to this, okay, solving simultaneously, right, I will then be able to find that x is equals to 1 and 5 over 13 and y is equals to 8 and 4 over 13, and therefore, okay, I will be able to get the coordinates, right, to be as such here. All right. So and that's it, okay, for this this question. Okay, so homework for this section, right, is going to be found in exercise 7.3 from your textbook, page 177 to 179. Right, questions 5, 7, 8, 16, and 17. Right, the deadline will be 22nd June. So I will see you next week. Okay, and goodbye everyone. I hope you have a good day ahead.